the research in Facebook, the face recognition, right? So after having this intensive course for 9 days, I believe you guys already gained so much of knowledge about machine learning and deep learning. So I thought it's better to give you an overview, how the people are working on it, and what are the next challenges. Maybe some of you might get inspired to work on it. So that's my objective. I'm trying to motivate you guys and join my community. Okay? So the face recognition. So I will start with this slide. So I think everybody has Facebook account, right? Yeah. How many of you are using it since last 5 years? Last 10 years, maybe? Okay. In the Facebook, in the earlier days, they used to have some options. Do you want to tag yourself? Or do you recognize this guy? Right? And now, they can automatically actually identify you. Right? So even some of your friends upload the picture on Facebook, and then they said, oh, you might be there. Do you want to tag yourself? Right? So how it has been possible? In the Facebook, you might be knowing millions of images are uploaded every day. Even you might have like 5,000 of friends. So they upload the pictures. Even you also upload like many pictures. So there is a very big database of faces, right? Still, it's able to identify you. So how it has been possible? So today I will also explain some of the underlying technologies, what actually had made it possible. And there is another applications. So in the smartphone, before we used to have some kind of fingerprint to unlock our phone. Now they have enabled this feature. Like you show your face and then it can unlock, right? But when your parents or your friends, they want to unlock it, it's not possible. But personally, I don't like this application, it's better to just press the fingerprint and then unlock it. If you get a call in the night, and yeah, it can still unlock with some other technology to utilize others, but it's a bit hassle, right? So anyway, the point is that how it has been possible, right? These are the two applications. There are many, numerous applications. So let me show you a snippet of newspaper from Telegraph in 23rd January 2017. So it's almost like 2 years back. And it's the news about Australia. They are planning to, make their airport passport free. It means you don't have to carry the passport. You just walk over and it identifies you, maybe access all the information, and then verifies whether you are you are a genuine passenger or not, or something else. So then you'll just let you get in. So can you imagine, what can be the advantage if such kind of technology is installed in the airport? Anyone would like to volunteer? So the advantage is that one is, it's like you don't have to really be in the queue, or you don't need to, they also did not need to employ, people are sitting there, like they check your passport, see the picture, and then they look into your face. Now these days, there is automatic verification also. So, it will reduces a lot of cost. If it's automatic, they don't need to hire the people to stay in the airport. Otherwise, it will be very efficient, right? We can just walk, and then we don't really have to wait for long. So my point here is that, such technology is helping our lives day by day. It's helping us, it's helping to make our life easier, right, and more efficient. So here is another picture. So she is, or he is maybe, I don't know. So anyway, okay, a policeman from China. And this is the news from the the birds, and then it's about like the policeman's specs are equipped with face recognition technology, right? The idea here is, if it's equipped, I mean, you don't have to really focus. I mean, if I have to look here and who is present here or not, maybe this equipped specs basically can tell me, I mean, scan it and then tell me, oh, this guy is present, this guy is present, and, I really need not, I mean, I really need not to bother about it. And this is used for security purpose. I mean, if there are some people who are suspected of doing some crime, and maybe it can help them to find the suspected people or identify them. And I didn't include in my slide, but have you heard about this Boston Marathon bombing, right? So the culprit was identified. I mean, the police were able to catch them in a very short period of time using such technology. They analyzed their video. Here, see here, there are so many cameras, right? Everywhere its camera is installed, and we are recording so much of data. Now, I mean, if we sit there and then try to analyze who is there or not, it takes ages for us. Now, if we can have a robust face recognition algorithm or the system, that can make our lives very easy and efficient, right? So apart from this, what do you think, like what can be the other applications? Does anyone work from any company here? There are some professionals, right? Okay, so are you thinking of using face recognition technology in any way? How are you thinking of using it? Can I get the mic? Okay, so one is attendance, yeah. So
so one is attendance. Basically, sales people in retail FMCG industries have to report their manager by taking a selfie, and GPS is also an important case key. I was in that location, and here is the proof. So before it was done manually. Now, with respect, because of face recognition, we don't have to have a manager just looking at images whole day.
Yeah. And others can be like, in the business, if you are doing some kind of business and your customers is there, and then you are offering them some service, and you can also recognize the emotions, right? Whether that guy is really appreciating what you are offering or not. So, I mean, see, the technology, how it is helping us. So, these are the many applications. These are the few representative only. So how this has been possible? What is the underlying technology that is making it possible? And yes, so in the face analysis, right? I mean, I generally would like to give this term, and it's not only me, many people give it. So it's analysis of the face, and there are several tasks. So one of them is face verification. So what does this face verification mean? So you'll take a pair of image, and then you check it whether it belongs to the same person or not, right? So she's a lady, she's Angelina Jolie, so we can definitely identify it. So our system should also be able to identify, tell us that, okay, this image belongs to the same lady, and this belongs to the different lady. So this is called face verification. So it's a function that takes a pair of face images and predicts whether it belongs to the same guy, same person or not. So another thing is like face retrieval. So this is something like, you'll have a database, face database here. So it's something like a face database in the Facebook or somewhere else, Then there will be a query image. So then that's your face query image. And then the task is that it has to compare with all the images over here, and then has to rank it. It has to sort it based on the similarity, right? So given this image, it's try to identifies the other ground truth image of this guy and ranks on the top. So this is Obama, so it is able to identify the other images of Obama here. So this is called face retrieval, right? So we are talking about the similarity between the faces, right? So from this picture, 3 pictures, so can you tell me Which is more similar? So how many of you tell AB? Raise your hand, please. Okay. How many of you tell AC? Okay. Why AC? Can you tell me why it's AC?
Actually, I think that it is both are female figure.
Huh? A and
C.
A and C female, yes.
A and C. They are female and they have similar faces.
No, it's actually the same lady.
Yeah.
Yeah, so that's good. I mean, who told AB? Who is for
That
AB?
was not my answer.
So can you answer me why it's AB? I mean, it's a bit surprising, right? AB. I mean, Donald Trump. How can I have a relationship between the similarity between Donald Trump and Angelina Jolie?
Anyone?
I think because both of them are shouting, and generally what the convolution neural network does is extract some feature from it, and the feature of their mouth, their cheeks, when they shout, they go up. I think the features will be the same, and they might be more similar.
That's true. That's true. Yeah, but I would say both of you are correct. It's because if I take care of I want to find the similar moods in the face image, then these two pictures will be similar because they are shouting, right? But if I want to go for identity, then definitely these two pictures will be similar. So what I'm trying to tell you here is that, the similarity of the images depends on what we are looking for, right? What we are interested on it. So then, if we just represent it with, let's say pixel level intensity, like some of my colleagues, they already taught you, right? In the last picture. They were also showing some hanging kitten, and then they are asking what's there or what is the similarity between these things, right? So my point here is that, okay, so the similarity between the faces depends on what you are interested on. Then how to learn extract such representation from these faces. That's the important thing, right? We have to make discriminative. Let's say if we are interested on identity, then the way we extract the feature from the face should be discriminative for identifying the individuals. And another thing is that if we are interested in expressions, then we should be able to pick the such features from the face so that they can help us to discriminate the expressions, right? So if you just look into these two pictures, and maybe this mouth area or this kind of area will be more interesting for discriminating the mood. But I never know. That actually we are looking for how to automatically learn such features, extract from the features using machine learning algorithm. So let me go to this term called metric learning. So this is a very famous approach for extracting such features, not only in the face, in the other application as well. So in the metric learning, here we are very used to with this alter distance, right? So here x and y are two vectors. Let's say we represented the face into the vector form, and then we just simply compute the Euclidean distance between them, right? With this thing, we will, if we take two images, we always get the same distance. Given that, if we take this simple pixel intensity, right? If that works for identity, maybe that doesn't work for expression or other stuff. So for extracting such features, this metric learning, parameterized distance metric learning is quite successful. Here in this distance metric learning, so we will learn this, it's something like Mahalanobis distance. You are familiar with Mahalanobis distance, right? Last time they taught it, right? This they projected onto this covariance matrix and then computed the distance, right? So this is something like this. So this let's say if these two are the vectors of face, we represented the face in the vector form and their dimension is D, and usually it will be very high, right? And then this is a matrix with the dimension D cross D, right? And this will be it should be at least semi-definite matrix because we are going to compute the distance, and distance cannot go negative, right? And then in this matrix, if we set all the elements 0 except for identity, I mean the axis, diagonal axis, and set it to 1, so that will be Euclidean distance, right? It goes back to this. Now, since it is semi-definite, so we can definitely decompose into its two-component matrix, right? So if we decompose into L, tau L, then what you can do is this matrix can have a very small dimension. So it's something like D cross D. Then again transpose of L, so it's D cross D. So if we multiply these two, it's nothing but M, right? Now what you can do is that if we do this factorization and project into this new matrix, decomposed matrix, what you can see here is that this is something like projecting on this L matrix and computing the Euclidean distance. So, I mean, the very first day, Azad taught you in the transformation matrix, right? Do you remember that? So it takes an input as a vector and project on the some matrix, and then again it generates some vector with low dimension. Why we are interested in low dimension? The one thing is that if we can compress it, then we can efficiently compute, right? We can efficiently compare the images. Another thing is that we will also select only discriminative features. Okay? So let me go back to this. I mean, apart from this kind of dimensionality reduction, we also, studied about another dimensionality reduction, which is called PCA, right? So in this PCA, what do we do? Here is, okay, this is the two-dimensional data here, right? Then we subtract it by mean. Then we bring it here in this origin. This coordinate, right? Then if you look at here, if there is a one axis with maximum variance, right? And there is also another axis here. So basically we compute select the axis where there is largest variance, and then we order them on the decreasing order of variance, right? So now here, if we just remove this principal axis, then this is how it looks, right? And if we only take this axis and project the data on this axis, so this is how it looks, right? So if we have two-dimensional data and we only take principal axis, then our resulting dimension will be 1, right? So you know about the PCA, right? So we can do similar thing in the face as well, right? So it's the face, and there are the eigenvectors that we computed. And then if we project it into this, let's say if we take 3 PCA, then our dimension will be 3, right? So what I'm trying to explain you here is that, where there are some methods which can, basically here also we plotted it in 2 dimensions, but here are some noises, right, which are far, far ahead. So with this kind of techniques, we can basically, get rid of such noise, one advantage of it, because noise always, creates when we are modeling, right? And we get more and more discriminative. That the direction which is better described, which better describes our data, right? So, but the disadvantage, how we are doing this here is that, it's simply unsupervised way. You take some training samples and then you compute this covariance thing and try to variance and select some eigenvectors. But, as I said before, we are mostly interested on selecting the discriminative features for different specific tasks, right? So how to find this direction for different tasks? So yeah, so some of the merits that we have, I mean the advantage that we have using PCA is that, yeah, it reduces some redundancies, I mean, some redundant information and noise, which makes us more discriminative, one thing. Another thing is that it also transforms the representation into the low dimension features subspace, right? And then to compute this, we don't really need to have some level information. Level information, right? Its image will be annotated by some labels. These are the advantages. I mean, you can simply compute. I mean, if you just get sample, we can compute the PCA. But there are some problem with this method as well. One thing is that we don't have level information. Why I am referring to the level is that, again, I'm reiterating, we are interested to, come up with the features that are discriminative or helpful to distinguish for our the tags that we are interested on. So I am showing some representative images. So it was supposed to be like, illumination highly variance in illumination, and then with the different pose. So if we have such kind of images and simply compute PCA, then the principal axis that we see here before, this may not correspond to the identity. It may correspond to this illumination or even pose. And then if we just take this, I mean, if we project our data on this dimension, then that will not be able to distinguish the identity, right? So it's not robust for this kind of challenges that we every time face. So how to get rid of this? How can we learn, how can we sample it actually automatically, such features? So for that, yes, there is supervised metric learning for face verification. The verification, as I mentioned before, like it's taking a pair of images and then predicting whether they are positive pair or they belongs to the same guy or not, right? So then what kind of supervision we can have is that some kind of similarity and dissimilarity, right? So for that we take, like, let's say, I mean, we projected this image into 2 dimensions, and then we have some annotations like this lady belongs to this, these are the same lady. So I'm talking about the identity now, okay? And this guy is the same guy here, and this guy is game, but these two are different, right? So now taking this information, I mean utilizing this, embedding this information in our metric, the transformation metric, we want to get, like, bring all this lady together here, this guy here, and then these people away from it. So it's something like we want to learn some parameter that basically, better satisfies, I would say, the constraint that we impose here. These are the constraint, right? So it's something like, okay, learn the parameter in such a way that I am imposing this constraint, like these are the lady, and this should be closer and this should be farther. So that should be first satisfied here. So if you just look here, these are closer, right? I mean, it's better satisfied here. So this is called supervised metric learning. So today we'll have a lab on it. So I would request you to focus a bit on it, and then it will make a bit more clear. So for this, commonly, I mean, in the face recognition, the commonly used constraint are pairwise similarity and dissimilarity constraint. One thing, another is called triplet constraint also. So I'll explain what is pairwise, what is triplet constraint. So pairwise constraint are like given a pair of images, if they belong to the same label or the same category or the same person, then they should come closer, right? They should be more similar than someone who are different. So this is Obama, so he should come closer after learning, and these 2 guys, they should go farther. It's also called must-link and cannot-link kind of thing. It's kind of, attractive and as well as repulsive kind of force. Bring the same label into the same space closer, and which are different, just push them away. So another is triplet constraint. Here is like, it's not clear. So one is called anchor, and anchor is like a query image, for you, right? And there will be another image which is a positive image, is called the image from the same label or the same guy. I'm referring here again identity, so it's the same guy. And then there will be another guy which is a different guy, right? So they use this kind of tuple, and then xi and xj, it's the anchor. This is the xj is positive and xk is negative. So then after learning, xi should be more similar, more closer on this subspace than xk. So these kind of constraints are used, right? So do you see any difference between this pairwise and triplets thing?
Sorry, I have a question.
Please.
What do you mean by hard negative examples?
Negative? Where in this?
Hard negative.
This, in the triplet?
Yeah, you say hard negative examples are selected.
Oh yeah. I mean hard negative. I mean that I was about to discuss. So this is some kind of, when they create this tuple. So basically they try to find the negative example, but which looks more closer to you. So negative example can be anything, right? So, but they try to find someone which is closer to the positive example. Yeah, in the feature space, yes. Yeah, that's true. I mean, because in the image space, it's not that already discriminative, right? So they do in the iterative way. Yeah. So that level of details I didn't want to go, but my point here is that, yes, they take 3 examples, and then one of will be the anchor, one will be the positive, and another will be the negative one. So yeah, so the only difference is that, yes, it's, I would say, like pairwise constraint, it's this very easy to collect, I guess, because comparatively, because if you just take a newsreader video, you can just take the frames, and then there is very less likely that other guys will be present there. So I mean, yeah. So in the pairwise, they actually do not consider, how negativity is. This would be different, right? And the pairwise, and the positives would be same guy. But in the triplets, referring to this FaceNet paper, they are basically a triplet. Generally, I guess they use some kind of KNN to find the nearest negative, and then they make a tuple. Maybe that helps to converge quicker, right? So the triplet is like it's a tuple. With 3 examples. That's how I understand actually. So, but if you want to converge your algorithm, it's always like if you take hard negative example, that really helps. So yeah, pairwise we can definitely collect. With this video, this setting, take some video of guy and then try to collect the frames and detect the face, and then from the continuous sequence, it's very likely that the same guy will appear. It's a naive approach, and then if you create the time frame distance on the video, then another guy will appear, and then you can just make positive and negative chaos. And actually, this kind of approach has been applied in some of the papers, and then they are able to, in a very weakly supervised manner, they are able to learn a very discriminative metric, distance function. So now, the thing is that I am going to explain how we can learn this projection matrix where the imposed constraints are better satisfied. And in this case, I'll take the reference of this pairwise similarity and dissimilarity constraint thing. And similar thing can happen, we can do it in triplets as well. So to learn this projection matrix, so basically what we do is we minimize this max margin objective function. So here Yij means plus minus 1. So that means whether the pair of image xi and xj belongs to same people or not, same guy or not. And then here this L is, DL means this is parameterized on this L projection matrix. So it's something like you project, this is something like here. So you project on this subspace first, and then both the images and compute the Euclidean distance. Okay? So this is the distance, we'll get it. And this B is called bias, this is called threshold. and then M is the margin, like how far you want to push it, right? So what is the difference there should be between positive and negative pairs? So if you imagine this at the end, then the distribution of positive and negative pairs should be. So we use stochastic gradient descent to learn the parameters. So can someone come in front and compute the stochastic gradient, this gradient descent of. So we take sample a pair of image and then we do basically project on it, compute the distance, and then we apply basically this condition here. No one?
You want us to compute the derivative?
Yeah, derivative of it. This one, because we will update the parameters with respect to it, right?
Yeah.
Just a derivative with respect to L. This is called bias. This is called threshold. We have to split the distance, right? So this is something. So there will be a threshold to split to, if something is also, I think maybe if nobody, I'm waiting for someone to compute this derivative and then I will explain what it is. So there will be some kind of distance to split positive and negative pairs, right? If something is greater than this, then it's positive. If the distance is lower, if distance is lower than some b, then it's positive pairs, and if it's higher than this, negative pairs. But we don't want them to bring very close, like we don't really want to have some very overlapped, much overlapped, right? Then it will be very difficult to, it may fail in the testing time much. So we want to set some margin so that these are pushed apart. Just a gradient, right? This take, maybe apply some chain rule.
Yeah. So inside the norm, it's linear, right? The Lxi minus Lxj, that's linear. And you just have to take care of the norm using chain rule.
Yeah. Should I move to the next slide, or I can get some answer? Guys, please focus on this algorithm, because if you are working in computer vision and if you are trying to do some kind of image matching application, trying to work on this algorithm really works. This is a proven algorithm. So try to understand it. You can apply it anywhere. Before deep learning, this algorithm used to be the state of art in face verification. Yeah, triplet is used, but it's trying to find some, as you said, like hard examples, right? So hard mining and then hard example mining and these things. So, but the advantage is that pairwise it has an advantage as well, right? If you have to find a hard example, negative, then you have to put extra effort, for sure. If you can do this, you can go for triplet. Yeah. I'd say more or less. I don't know, but the performance should a bit higher on triplets, but there should not be very big significant. If you do not really look for this hard example. And yes, so how does this perform with comparison to the PCA? So I was criticizing about the PCA, right? So not really, but there are some limitations. It has both advantage and disadvantage. So we did some experiment on this LFW, is called leveled faces in the wild. It's a very popular benchmark in face recognition. And this has almost 13,000 images with 5,000 different people. And we did some face retrieval task, and then we compared the method. So this is extracted from one of my work. So actually this is my figure I generated. So yeah, we can basically see there is a very big jump in the performance, right? Because the parameter that we learn using metric learning is, optimized for the tasks we are interested in, right? So now I'll come with, in summary, like we discussed about PCA as well, and then metric learning, right? So how does it work in the pipeline? Is that we have an image, we compute some handcrafted feature. So handcrafted feature, you know this, right? Shift, that's handcrafted feature, right? You have heard about shift, right? So there are other features also. Maybe you can explore on it. So before, this deep learning getting popular, these handcrafted kind of features were very popular and successful. So it's something like shift is there is local binary patterns, there is Fisher vector. So that I could not cover it here. But you guys can definitely explore on it, right? It's basically this handcrafted means they don't really think about the task. They just try to compute some higher order statistics out of pixel intensity, right? So this kind of handcrafted feature we can compute, and then we compute PCA and project into the PCA subspace. Then now we compute the L2 Euclidean distance and compare the phase. Compare the phase. So similarly here also what we did, we computed the handcrafted feature, and then we did metric learning, projected on the metric learning subspace, and we compare the phase. So what's the problem here? Right? There is definitely a problem. No? This is mostly relying on this handcrafted feature, right? So if you it's compare, if there is something already we miss so much of information, then we cannot, go beyond its limitation. The thing is that, if something is error, then we cannot propagate it till the image here, input space. Then we don't know what to pick from the input space also. Right? So this is the problem in such learning algorithms. That's why the deep learning has advantage over it. Right? So deep learning, it's not only about the layers. It can go from end to end. It starts from pixel level, it goes to the end, and back propagate the error till the input space, right? So now, we will jump to deep learning, So it has this such advantage that I mentioned before. Definitely it has more nonlinear layers. The metric learning that we did before was a linear projection, right? But the face classification or the analyzing the face is not a simple problem. It's a very highly nonlinear problem. To model such problem, we definitely need to have a complex model or the nonlinear model, right? That you guys already know about this linear, what is a nonlinear model and what is nonlinear model, right? So deep face is one of the, it's one of the prominent papers. It's the first paper actually on using the face, in at least in the modern research now. So all these layers, right? So I think I will need to explain it, but I'm not planning to explain it as well. So it starts with the image, it goes through convolutional and max blooming layers and all this, that. And at the end, what it does is, there is a softmax layer at the end. Do you know what is softmax layer? Huh? Can you? So if there are 100 classes, then what will be the dimension of softmax layer?
Who wants to speak?
Sir, 1 by 100. 1 by 100.
Why 1 by 100?
Sir, it will predict the probability for each class and list the probability of F.
But that's a uniform distribution, right? We don't want to do that uniform distribution. Yeah, you are right. There will be 100 outputs, but we want to make a prediction in such a way that the probability of that particular class will be peaky and other will be flat. Take an image and it make a prediction and it predict which human being it belongs to, which candidate it belongs to, identity it belongs to. But if we have to take some new identity, it cannot compare, right? So if there is something new one, the one who has not appeared during the training, so what will make prediction? It will make to one of the classes, but cannot, right? So then what they have to do, what they did is they took this fully connected layer, last connected layer, as their features, as a feature of image, and then they further run another classifier, linear classifier or other classifiers, to match the people. So there is a bottleneck, like there is so many, there is a multiple stage, right? So to tackle that problem, basically, FaceNet proposed to learn this embedding here itself, the face representation here itself. So that once you train this thing, you can simply pass two images, extract this embedding and compare it, compute the Euclidean distance, and you are done. Right? So it uses, to learn the parameter, it uses again this triplets. The triplet is anchor, so it's the one query image, I would say, right? And then there is a positive image for it, ground truth, and there is a negative image. So after learning, it went, this distance, this Euclidean distance of this embedding is minimized, but the distance between anchor and negative is pushed further, right? Yeah, so the main objective of this architecture is to minimize L2 distance between the same identity spaces representation. And another thing is that it directly transforms this image at low dimensional space. So basically this dimension is 128 only. In the previous architecture it was 4096 dimension. Right? So you guys can go into the detail and read the paper actually. So I just wanted to give you some kind of overview, and then why I choose only these two papers. There are many others, right? There is called BGG 16 from Oxford. There is called BGG 18 from Oxford. So there are so many architectures there, but fundamentally there is not much difference. So, but these two looks a bit different, the way they learn the parameters. Yeah, so again, this uses triplet loss to minimize the, to learn the parameters, and then, it minimizes this max margin objective again. So it's here. So this is anchor, this is a positive, and, this is anchor and then negative. So they want to minimize these differences, but they want to add some kind of margin here, right? It means the positive, the distance between these two and this anchor and positive and the anchor and negative should be separated by some margin. Okay? And again, they use some kind of these hard and negative examples, and they mine it during the training. So, I think that's not really important to discuss now, but I hope you got the idea. So I would suggest you to read this paper. It's published at CVPR 2015. Yeah, please.
Yeah, is the margin also a variable in your optimization?
Here?
Yeah.
I think you can keep the constant as well as you can learn as well.
Okay.
Yeah.
Okay.
So for example, during the metric learning, when I did my metric learning, I used to also learn the margin. Margin is usually kept constant. It's kept constant, yes. But bias I used to learn, slowly moving the threshold.
But I guess you could learn the margin using cross-validation as well.
That also can be done, using, plotting this ROC curve and this thing. But this margin is to push the positive pair distribution and negative pair distribution, so that all the positive pairs, all the positive examples, they will be closer and then they will be a bit farther from this thing. So this is something like here, I rubbed it. So I drew on distribution, right? So this is something kind of margin here, so mean distance from here. So this is margin or alpha or m.
So I have a
please.
different question.
Please.
So in terms of the comparison between your metric learning approach and this FaceNet, what is the comparison?
It's a deep network and that's shallow network. That's the difference. Fundamentally, I guess.
But in terms of the performance.
Performance is very much different. It's if we have to. In the metric learning, we have to rely on this handcrafted feature, but we can use CNN as well. For example, we can use this CNN feature. For example, this thing from VGG, not VGG, this deep face. And extract this and learn the projection matrix using triplet. So that is what exactly they are doing it, right? So they embedded this triplet thing at the top layer of their network. Yeah, please.
So in that deep learning architecture, So in deep architecture, what sort of architecture are you using? Like we can plug in anything like Inception or AlexNet or anything, or is our choice, or is that architecture given by FishNet?
That's actually, people are exploring, this learning the architecture, optimal architecture of deep network, and then the hyperparameter, which is the optimal one. This is also one of the research people are doing actually. I mean, how to automatically design the architecture for a specific task. So Google is doing, they are, using reinforcement learning kind of things to find such architecture. But yes, people are trying, different things. Yeah, please.
I think his question was like, what is the case for FaceNet? Is it their own architecture, or right? Is it?
You can plug in Inception or any architecture that we like.
No, these guys basically they design it, right? They design this architecture to address the problem that DeepFace has. DeepFace was published in 2014, and this paper is published at 2015. So when we do the research, what we do is, what is the problem? What are the problem that existing method have, right? And they try to address it. Okay, this architecture, DeepFace, actually doesn't learn the embedding, right? And maybe they thought of how about learning the embedding itself in the network. For example, here, they compute this layer as a feature, but these features are not optimal, If we go into the diff and see, there are so many zeros here, and most of these are zeros here. And then it has to, they have to train another linear classifier or other method to make it more optimal. But here, this is the embedding, so it's a continuous values they learn, and then they can be directly compared.
But they have also changed, like the previous one was using loss inclusive variance. So FaceNet is using triplet loss. So
yes. So again, I mentioned you right in the beginning that the objective function, the similarity between the images depends on what we are looking for, right? And if the objective or the objective function does not align with what we are trying to do, then these features will be suboptimal. So in the previous case, they try to predict the identity, right? But the end task is to compare the image, right? So it's better to learn the parameter in such a way, that actually match with what you are interested on it. Then your parameter will be optimal. This is kind of some kind of indirect relation with the identity, right?
So I think what I would like to point out to is there's a strong similarity between this approach and the skipgram embedding I talked about. So would somebody like to say what the similarity is? I think it's also useful, in this part of this course to think in terms horizontally, in terms of the similarity across different types of machine learning applications. Here we're talking about face recognition, there we're talking about similarity in meaning of the words, right? So in the skipgram embedding, if you remember, we have a word, right? We have a context word, and we have a negative context word. And we want the context word and the target word to be similar, right? Through the embedding. And then we want the negative words to be dissimilar, right? So if you remember, I drew the cost diagram there. So essentially what's happening here is very similar to that.
So I would tell you one example. I'll try to bring some analogy, right? For example, okay, if you are preparing an exam for science, but if you read science magazine also, it may help. But it's better if you just, focus, try to master your coursework, right? And if you can also read so many science magazine related work and this thing, still you will get the knowledge. But if you really want to appear in the science exam, maybe if you just focus on your coursework, maybe that will make you more efficient, and then maybe you can achieve more, right? Is it something like there also? It's here is something like it's predicting, given an image, whether this guy belongs to this or not. Okay, it's identifying it. But it's not somehow relating, comparing the negative examples, right? It doesn't much care about it. It only cares about the images from one person and tries to make a correct prediction out of it. But it ignores like how different it is from other guys. Right? Yeah. Yeah.
So like how does it work for identical twins? Like
Oh,
whole
yeah.
face recognition thing.
Hmm?
So like what are the determining features? Can you give us like some intuition like for identical twins?
Oh, I mean, this is a really, really challenging problem. This is a challenging problem, right? You know, you pointed the right thing, but I really cannot handpick the feature, right? But if you have to design it, definitely, I think we have to collect more and more twins pairs, right? And then that will be a hard negative example, you know. We were talking about hard negative, right? So the twins will be a hard negative example. And if you train your model to discriminate such thing as well, then your model will be more robust. That's the reason, I mean, this FaceNet is also looking for this hard negative example here.
So like right now if you are comparing with human level, like if you pick the best model from like face recognition, like is it able to identify between identical twins or not right now?
It can, but not in many cases, I don't know. Because we don't have such benchmark to compare, so, but there is one small, but definitely it will work, but the way it works for other people, the performance will definitely go down because there are very difficult examples. So I will show some of the example, what kind of images it's not able to classify here.
So also like before we can sort this out, like can we use it for like security purpose, like the Australian airport example you get?
Yeah, that's the underlying thing, right? This is the technology behind that.
Okay,
I mean, may not be that exactly this one, but similar technology. So what people are trying to do is how to make the model more and more robust, you know. So that's the purpose, yes. Okay, shall I move ahead? Okay, so now they also did the experiment on the same benchmark, right? So as I mentioned before, now its performance is 99.60. Did you see the difference between these two? And this human is 97.5, but this is on the cropped image. It's not like exact image. The head was, this part was cropped and shown to the human, and then do you recognize these two people, and then are they the same individual or not? Now, yeah, here is your question, right? So where this FaceNet got failed, right? So here, I mean, these are some hard examples it could not verify. See? So this is, it rejected as different, but they belong to same people, right? If you see here, I mean, you know, this guy, I mean, this pose thing is making difference, you know, some kind of occlusion is making difference, right? Maybe some kind of makeups is making also difference here, right? And then, yeah, it's difficult, you know. Even if it's same for us, right? If someone put on the makeup and then removes the makeup, it will be difficult to recognize. Yeah, and so this is the thing, right? This is the occlusion, and yeah, so false accept. I mean, this model predicted that these two guys are the same person. See, and they look more similar, right? Even it's difficult for us somewhere. So these are the hard examples, you know, where it is failing, and that is what your question is. I mean, in the twins also, I mean, they will look exactly the same, but they are different people, right? So now, I mentioned to forget that, I mean, you know, this FaceNet almost used 20 million of data points to train their model. 20 millions, I mean, which is a lot. And then this Facebook, they use 4 million data points, data examples. So this many data, I think we cannot collect, right? It's very difficult for us. It's because, I mean, we don't have that kind of crowdsourcing like Facebook. Everybody, I mean, gives their data, upload their data. We don't have that. I mean, and it's illegal to, I mean, you know, to collect others' data, use the biometric information also. Now, how to make it accessible to everyone then, right? This is also another question. So now, I mean, okay, before jumping into that, I would say like, yeah, before GPU, if there was no GPU, it would not have been possible to train this model. Would have been, but it could have taken ages. So computing resource is one thing. Another thing is that data hungry. It takes a lot of data. So now I won't be jumping into this computing resource because it's something different. So I will focus on this data hungry thing, which I'm working on right now at Imperial College London. So I will share some of my experience, the research outcome that we did there. So before that, I would like to play a video. Maybe you want to, is it Tom Hanks or who is this guy? Tom Hanks, yes. So, this video describes about this morphable model for synthesis of 3D face, and which actually we use to synthesize
model
image.
Is derived from a data set of 200 colored 3D scans of faces.
So these are the scans
Individual
of real
faces
image.
are combined into a single morphable model by computing dense point-to-point correspondences to a reference face. A modified optic flow algorithm establishes 3D correspondence automatically. The morphable model combines 3D shape and texture information of all example faces into one vector space of faces. We can form arbitrary linear combinations of the examples and generate continuous transitions.
So I'll stop it here. So
starting from the average face, individual original.
Yeah, I just stop it here. So what they did is, I hope you understand is they took this 3D scan of the human face, right, the real face, and then they do the registration within the optical flow. Even Azad and Bishes, they taught you, right, registration. So guys, whatever it is taught here, so just keep it in mind where it is used, right? They do registration, they find these coordinates, vertex to vertex correspondences, and they come up with one module, right? And they do, do decomposition, PCA decomposition. Here comes this PCA decomposition. And then we also discuss about this different axis, right? So each of the axes carries different traits on the face. And then we try to play on this thing to generate different images. That is what he is explaining here.
Faces are caricatured by increasing their distance from the average. Forming the average for male and female faces separately, the difference can be added to or subtracted from an individual face to change the perceived gender.
So from that morphable model, we can generate so
Other
many
facial
different
attributes,
face,
such as the fullness of a face, can be manipulated in a similar way. From a labeled set of faces, the characteristic changes are extracted automatically. In our model, they're controlled by a single parameter. Differences in facial expressions captured from another face can be mapped to any individual. We
So
now
the expression is also
reconstruct 3D
changed,
shape and texture in order to animate a face, given only a single photograph of a person.
Okay.
First, we manually
I think
align the average face.
It's not very important for me now, that what I'm going to explain. So maybe if you are interested, you can watch it later. Or you want to watch it now? Okay.
To the target image, roughly estimating position, size, orientation, and illumination. Then a fully automated algorithm finds the best reconstruction of the face within the morphable model. 3D shape and texture are optimized along with parameters such as size, orientation, and color contrast. The output is a high-resolution 3D mesh of the face. It is an estimate of 3D shape and surface colors based on a single image. Additional texture extraction improves details in texture. The reconstruction can now be rendered into the image, and a whole range of facial variations can be applied. Here we simulate weight gain and weight loss. Facial expression can be post-processed in images, forcing a face to frown or to smile. From this image, we also estimated 3D shape and texture and combined the photograph with 3D computer graphics. Cast shadows of novel objects are rendered correctly into the scene. Illumination conditions can be changed and pose can be varied to some extent. From a single black and white image, we obtain a full estimate of 3D shape. The result of the matching procedure includes an estimate of surface color, since the morphable model contains color information. Finally, we show the application of our model to a painting.
Okay. So there are many videos to come yet, okay? No worries. Oops, that is what I didn't want to do, okay. So, in the video, we show like there is a statistical model, morphable model, right? So you can just change them. You can vary on the different dimension, right? You can change, you can have a different people, you can even change the gender, and you can change also the expression, and even the pose, you know, you can just move it, right? So these are the face, right? So this we can easily do it. But the problem with this thing is that they are not realistic enough. Right? And then what we are trying to do is that can we generate such images and then so that we can just augment, we can use this to train the deep network. But if we simply just take this image and train the deep network, it won't work. Can you guess why? Why it doesn't work? If I just take this kind of face image with the different identities in the same number, like 4 million of face, and the train network, will it work for us? Yeah. Exactly. That's domain discrepancy. Yes. The distribution of the feature in these images and our face is different. So if you train on one domain, it's called domain adaptation problem. This kind of problem is called domain adaptation problem. So there will be some kind of domain discrepancy, right? So it won't work for us. So now, how to fill this domain gap on these images so that we can use for our purpose? So that is what we did, one work at Imperial. So this is the problem. So okay, this is the first row, is the synthetic images, and second row is the images generated by our system. So see, this looks more realistic than at least these guys. Right? And another important thing that you have to notice here is that the condition that they have, in terms of like even the expression and lighting, that is preserved on these images. That is what we want also. Because to make our face recognition algorithm robust, we need many examples from same identity in the different pose and expression and illumination. Right? So we want to utilize its flexibility, its strength to generate these kind of images. Then we want to translate them into the real domain so that we can use them to train our model. Okay. So, okay, I mean, this is, I already explained this thing. It's a definition, what is the problem. And these are the two works, pixel to pixel, it's pix to pic, and cycleGAN. These are some of the related work, I mean, which inspired our work. And yes. So this is our work, and this is published at ECCV 2018 this year. So here, what we did here is, okay, see these are the synthetic images from 3D So it has the parameter identity, expression, pose, and then this lightning, yes, illumination, right? You can play with this thing and you can generate many images like this using this renderer. Now this image is how to translate into the real domain, right? So for that we use GAN. So everybody knows GAN, right now? Yeah. So there is a GAN, this is called generator. Huh? Any problem there? Okay. So here is like, it's a generator, so and then here is a discriminator, right? So what we did is like, we took these images here. Usually this generator used to take random noise, right? And then people started using this, he started making its condition on different information like some images or text or something, right? So this is the generator. So we took these images and then we trained this model in such a way that, we propose this method to learn, translate this image into this real domain. So for that, I mean, we have a discriminator. That's the standard GAN, right? So generator and discriminator. But this only cannot help us, So we are translating from this domain to another domain, and we are going through so many nonlinear transformations. So the attribute that we want to preserve here, we are much more interested on these attributes. This is called, how lighting is this, what are the poses is this and this thing. So we want to retain those things. For that, to make this happen, I mean, simply these two won't help. So we propose to, add another generator, which basically can translate from this image, the synthetic real image back to this, this 3D faces. It means it somehow maintains the cycle consistency. I mean, this is also not a novel idea, but cycleGAN works on this thing. But it also has some kind of problem with the cycleGAN, Here, I mean, you translate it here, and then you come back. I mean, there is nothing to, these are random. If something is randomly initialized, it really, it really doesn't work well. I mean, we'll compare this performance on our experiment. So to avoid that, I mean, there is, it's called like inability to maintain the transitivity. So it goes from here and here, from one hop to another hop and another hop. So I don't know if it makes you clear, but anyway, so there is some challenges. So what we thought is like, we take some kind of pair of this 3D and real image and try to learn some initial parameters on this thing so that it can better translate it back and maintain that transitivity kind of thing. And that actually helped us a lot to improve the quality of image. And another challenge is that, so we translated here, but we want to preserve the identity also, right? Because these are the synthetic image. When we translate it, maybe we will lose the identity. Because if we cannot maintain the identity, then we cannot use it to train our face recognizer. That's why we also propose to use this loss called set-based loss. This is something like similar to, I would say, just to understand, make you clear. In the pairwise, there were two images. So if there is more images, then it creates a set, right? And then we want to maintain that set-based loss means like there is a centroid and then all the images belonging to this set have a similar embeddings in the, and that embedding is computed by this pre-trained CNN. So I don't know if it makes clear to you, but you can read this paper if you want. So that is what we did, and then so we were able to augment this synthetic images to train the network, right? So here is VGG. It's called Visual Geometry Graph group, right? From Oxford University. So they have collected this 1.8 million data points. So these are the real images, right? And then it's mostly used to train the model because it's public. Facebook doesn't make it public, so we cannot use their data. And then this is the performance on the face, this LFW. And now these are the GAN faces, means like this is the images generated by our method. And we generated in up to 5 million and augmented with original data and trained it. There is some improvement in the performance. But it's small, but it's already saturated. This data set, 1.8 million is already big data set. And then we wanted to check if we have a limited access to the real data, what happens? Is it going to be useful or not, right? It's a marginal improvement only. But when we had limited data, it's something like we took 20% of the image from data from BGG, 50% from BGG, and 100%, right? So when we were taking only 20% of the data, BGG data, and augmented our data, so actually there is an improvement in the performance, up to 2% or more than that even. So if we have scarcity in the data, then we can definitely use our data and augment it, train it, and then improve the performance. Yeah. And this is the evaluation of the data set. So this shows the proportion of real data and augmentation data, right? See, our proportion in comparison, if we take only 500,000, the proportion in comparison to the real data is, our data is very small, so we cannot see such significant improvement when we take the full data, right? But if we have limited data, like it's, this performance improvement is significant. We also did some kind of qualitative evaluation, so maybe it will give you some idea how to, how do we do the research and then how do we evaluate your method, right? So if you propose something, then you should do lots of experiment to, assert that yes, my method is better than yours, Otherwise, people won't accept your papers. They won't invite you in the conference. So we wanted to show that, yeah, this is the distance distribution. So I can relate with the distance distribution also. I was talking before now. So this will be the kind of distribution, This is the Euclidean distance distribution between positive and negative pairs. So this green, here are three different data sets. So this is 3D without translating it, without transforming it into the real moment. We computed the CNN feature of it from the pre-trained CNN, and then we computed the Euclidean distance. So see, there is much overlap between positive and negative pairs. So it means they are not realistic enough, right? And then this is our images distance distribution. So it's quite separated. Yeah, this is a positive pair, so they are closer to 0, and this is negative pairs, they are far from the 0, and there is a margin. So if you see like the margin between this, from mean to mean, almost it's 1, right? And this is the BGG phase. So BGG phase is even poorer than ours because they were collected in a weekly supervised manner. So there are so many noise. Now some qualitative results. So I don't know if you can see it clearly. From that screen it's okay, but here, So we want to show some kind of synthetic images that we generated. So these are the 3D data, and with different expressions. This opening the mouth is there, closing the mouth, different pose. Someone is looking like this. It's the same guy, but it's some images are in the profile picture and some are frontal, right? So then, how it looks when you pass it through our system, See, these are the real. Don't you think they are more real? Do they look like us or they look like some alien? These people never exist in the world. Yeah, these are not real people. Yeah, but they look like human, right? Like us. Yeah, and Yeah, so see, and then the thing I want to highlight here is that our method is able to preserve such kind of expression and even the pose on the translated image. That what actually we're interested on it. Yes.
Have you ever thought about like introducing some kind of more flaws so as to make it look more realistic?
Can you please?
1 second.
So you look at these faces in the images and they look like really symmetric, right? So
They look like, sorry?
the faces look really symmetric. Symmetric, yeah.
Face is always symmetric, no?
Yeah, but like research has shown that human face is not exactly like 100% symmetric. So introducing slight flaws in the images might make it look a little bit more realistic, maybe.
Okay, I mean maybe we can use I think if we generate like, that unsymmetric face on this 3D domain, maybe that will get reflected on the translated domain, I mean from our system also. But aren't the face symmetric? I mean, we always assume that face are symmetric. Okay, good. That's good observation actually. Thank you. And then here are some more images. I mean, why we did it is that, in the GAN there is some kind of mode collapse kind of problem. So the mode collapse is like for a given different inputs, it will map to the same output. So we wanted to see whether they can, our method is like robust to that or not. So what we did is that we slightly, in the morphological model, you remember that? We can slightly change the identity of the people and then go from one to another, right? So we wanted to see like if we change this identity from like one to another and then how does this thing appear on the translated domain, and then we also saw such reflection, and that also further validated that our models, I mean the method was robust to this thing. So yeah, I mean this is what I showed you before. I mean this also can preserve this kind of thing. And we did our further experiments on this, how are they, I mean they look similar but their nearest neighbors should not be same. Right? If you take a picture of ours into the same different time, then if you compare it with the other images, I mean with our image itself also it looks different, right? So we wanted to look into it. So yeah. And we also compared with our competitive methods and then, any questions? Are we running out of time?
Deep video portraits enable photorealistic reanimation of portrait videos. We are the first to transfer the full 3D head pose, facial expression, eye gaze, and eye blinking from a source actor to a monocular portrait video of a target actor.
So I just stop it here, okay? Maybe you'll be interested on video, not me. Anyway, where is it? So basically what they are doing is they are transferring the style from one image to another image, I mean the video to another video. That was something similar to what he did, but we did it on the still image and they are doing it in the video.
Given an input video, we first track the source and target actors using a face reconstruction approach. The resulting parameter vectors represent meaningful semantic dimensions, such as the head pose, facial expression, and eye motion. These can be
Yeah, this is a really simple idea, but it's really interesting. This kind of thing, they fit into this 3D right? I showed you before. And then this 3D will have different parameters, as I mentioned to you before, right? And then what they do is simple. They transfer these parameters to the target, this yellowish. They transfer it into this, keeping all the things same. And then again they use the GAN to,
directly transferred from the source to the target. Next, we render synthetic images of the modified target actor rig. Finally, we employ our novel rendering to video translation network that converts space-time volumes of such conditioning input into photorealistic video portraits.
Okay, so this is the basic idea only. So I will stop it here because you may watch it later. And then I will show you again since we are running out of time, so let me show you another interesting thing on top of it. How people are getting innovative, how they are utilizing this technology to generate the revenue. That's also going to be very important for us, right? So we do research, we do come up with the different products, I mean the ideas, but how to commercialize also. So you guys can think about it also. I mean, so I'm showing you one video how people are getting innovative, I mean, using this technology to make a commercial product. Oh, not this one. Yeah. So this is Synthesia, is a company based in London, and one of the founders is the co-author of the paper
I'd like
that
to
I showed you
demonstrate
before.
how Synthesia technology can make me speak 7,100 languages fluently. Why don't we rewind this video and I'll show off my language skills.
Nous vivons dans un monde plus connecté que jamais. Mais la langue reste un frein, surtout lorsqu'il s'agit de contenu vidéo.
想象一下，如果名人们可以用当地母语去和自己的粉丝们沟通，又或者说你翻译的内容帮你打开了一个新的市场。
Eu gostaria de demonstrar como a tecnologia Synthesia me permite falar 7.100 idiomas fluentemente. Por que não retrocedemos este vídeo e eu lhe mostrarei as minhas competências linguísticas?
So, you know what is happening here? Huh? So what they are doing is that, we watch dub movie, right? So, but the lip sync is same thing. And then, they speak in our language or Nepali or Hindi or whatever, but the lip sync does not synchronize, right? So what they are doing is that with the language, they are changing they are transferring this, style from native speaker to the actor. So it looks more realistic. So, if we can see one day Hollywood actor, maybe Leonardo or someone is speaking in Nepali, and he speaks like us, then don't you think it will be really interesting? Now, if they can make it, it's $1 billion project. Thank you. So, be innovative.